To wrap up today, I want to do one little cute thing, which is to look at the actual code and behavior of Java's HashSet implementation. So I want to note that something I didn't really truly believe until I got really comfortable programming is that all of this stuff is just programs. And I can go look at the HashSet code here, and I'll get, this is the actual code that Java uses for the HashSet. And one of the things that I can find if I go looking through this code, I mean, there's some things I haven't talked about, like the transient keyword is not important. What we find is that the actual HashSet is encoded, or it's stored as a hash map that goes from the key to object, and the values are just not used. That's what it actually ends up doing. I'm not going to show that in the code, but it's just a map. Okay, so if you don't know how hash sets are done in Java, we have to know how hash maps are done. Okay. So then we can go, of course, looking at the hash map code. And I'm going to search for some brackets. That's not the one I want. Here we go. This right here is the hash table, right? So what is it? It is an array of linked lists. And these linked lists, how many are there? We could go dig that up. It turns out it starts out as 16. There's 16 linked lists at first. And you could look at all the code and see that indeed it is a linked list, usually. And I'm not going to dig into there so much, but I'll say that all of it's here. Now this hash map implementation is a lot longer than the one we have for our lab. This one's a couple thousand lines long, but it's industrial strength. And so what I'm going to do here is give you some insight into what it is that it does that's a little bit fancy. Let's make sure there we go, good. So reading the code, one of the things you can find is that the hash table starts at size 16, and that it doubles every time n exceeds the load factor. And the default load factor is 0.75. So n over m should never be 0.75. Okay? And so you can go find those facts in there. Maybe control F16 and find it. The other thing you can find is that the reduce function is not just mod n. It is the hash code. This is something called XOR. The hash code right shifted by 16. And then it is and n minus 1, which it turns out is the same thing as mod in this context. Now I'm not going to go into this function in any detail. I'm just letting you know what's there. I'm happy to talk about this at office hours, why they use this specific function, but it's not important to us. It is very close to mod, just a little different, okay? So what I did is I wrote a class called HashSetProbe that uses the reflections library to get access to the private variable. So remember that I said that there are exceptions to all these rules. So even though that data structure, the actual array variable is private, this code I wrote in this file that maybe I'll put on GitHub. It's called a HashSetProbe. And what it does is I'll just give you a rough picture. When it's given a hash set, it gets the field called map. So remember a hash set just has a map, and that map is private. And so I use the reflections library to say, you're not private anymore, you're accessible now, okay? Then given that hash map, I say hash map, give me your table. And you're not private anymore either. And then I'll get that map, and then I'll print out every time we get a resize, we'll print out the resize operation. That's the idea, okay? Now I should note that if you try running this on your own, it will not work because Java has a little bit of protection against people messing with the libraries using reflection. It's something they call strong encapsulation. The idea is like someone really shouldn't be messing with it, so the language has special exceptions saying reflections doesn't work here. But Java's just a program, and it has options. And one of the options you can give it is a command line argument, which I'll show you briefly in case you ever play around with this. If I go to the project structure, and I look here in the project, where is this thing? Oh, actually, it's in the run settings, that's right. If I look in the run configuration, I have here a virtual machine operation where I say opens. We're going to open all of the Java util things to any class that asks. That's basically what you can read this as. Not super important. I'm just mentioning this in case you run it and you get an error. So if I run this code, though, what I will get back is it's running. It's adding things to a hash table, or hash set, I should say. And it starts off at size 16. But once it gets 3/4 full, so what's 3/4 of 16? That would be 12. And once it exceeds that, Java uses a greater than, whereas I used a greater than or equal to in my lecture, it will double the size and we get to 32. Once we get 3/4 full of 32, we go up to 64. 3/4 full of 64 is 48. We go one higher, we double, and so forth. Okay, so it's just using a doubling every time. Now, one thing I found interesting, I created this semester. I did not anticipate that the bucket sizes would be, that the number of buckets would be a power of 2. For reasons that I don't really want to explain, but I was a little shocked by that. Because I always thought of it as that was an example of a bad strategy. But the reduction function that they use avoids the problem that I foresaw. Okay, that's not particularly important, but my point is we can look and see exactly what the hash table's doing, okay, if you really want. That's kind of fun. Okay. So what we find is that n over m is never more than 0.75, which means if the items are evenly distributed, the average list has 3/4 of an item. So a lot of the lists are going to be totally empty. And that's part of the reason that Java's hash table implementation is going to be pretty fast. Okay. All right. So what I'm going to do now is run a little simulation back in our visualizer to get a sense of what happens when the load factor is kept to 0.75 or less. So I'm going to go back to this visualizer and I'm going to change this up. And this time, I'm going to show you what happens if I have 3,000 buckets, let's say, and there are 2,250 items. This is basically the worst case for Java's implementation. It never gets worse than 2,250 out of 3,000 items. And so if I run this visualization, this is basically what a Java hash table looks like as it's running. Okay. Now it does some resizing, so it's not quite a fair comparison, but because what it starts with is size 32, then 64, then 128, and so forth. But what you'll find is that once a hash table of size 3,000, that's their 3,000 lists, has 2,250 items, none of the lists have very many items in them. Like, I mean, if they're evenly distributed, it would be either 0 or 1 item in every list. But what happens in practice is the biggest list ends up with around 5 items if the items are totally randomly distributed, okay? So the idea is I have 3,000 buckets, I throw 2,250 items into buckets randomly, and the bucket that has the most turned out to be 5 in this case. Okay, and there's a bunch of buckets that will be empty, but that's not so bad. And so what that means is that it doesn't really matter how the buckets are implemented. They could be an unordered array, an ordered array, some kind of more exotic data structure, but there's only 5 things, and looking at a bucket of 5 things is going to be pretty darn fast. Now I will say just a bit more about this, which is in that simulation, it looked like around 5 was the most items in any particular bucket. And so I guess I'll tee you up for CS70 to say that in that class, you'll derive a precise mathematical characterization of the length of the longest bucket. This is the balls into bins problem because bins and buckets are 2 different names for the same thing. And you could basically show that math to show that the worst case runtime for any operation is going to be the number of items in the longest bucket, and it's a bit worse than constant. Okay. Now I'm not going to say much here. I'm going to defer it for CS70. But if you're curious, like why was it 5 and not 2 or 20? It's a CS70 problem. Now the very last thing I want to say before I go is if I go back into the code for a hash set, I'm going to actually do this one. Or for a HashMap, and I control F red black, you'll see that there's a lot of discussion of red black tree links. Okay. Now this is still HashMap, so you might be wondering what on earth is going on here. Okay. Well, the reason that there's hash maps going on here is that Java has an extra optimization, which is that, as they describe it, the map is usually a bucketed hash table. But when bins get too big, let's say you have a lot of collisions, that's lots and lots of items in one bucket, what happens is that the bin actually gets turned into a red-black tree, okay? Most of the bins are just normal bins, just a linked list. But if it detects that there's some imbalance, it will automatically turn things into a red-black tree and hopefully get better performance that way. Well, it'll be guaranteed better performance if the keys are comparable, so we'll be in good shape, okay? Now, this is all well beyond the scope of the course, exactly all the strategies used for here. But I just wanted to point out that if you just glue together the different pieces of our courses in clever ways, you end up getting pretty close to the industrial strength implementation that the HashSet uses in Java. So to flip Donald Knuth's quote on the head, where he said the most beautiful algorithm is not the most useful, I'll notice that the most useful algorithms, like this somewhat ugly 3,000 line long hash map, not exactly the most beautiful, but it sure works pretty well. All right, that's it for hashing officially. And so thank you everybody for your patience if you're waiting for this re-record to go. But I just wanted to get everything totally right because I felt like my rush job that I got in lecture yesterday just wasn't up to my quality standards. All right, that's all I gotta say, and I'll see you next time.